The kinetic theory deals with how gases move around. Kinetic means moving. So a few things you need to know about the kinetic theory. It pretends that gases consist of hard spherical particles as just a way to help us understand how gases work. It explains ideal gases, an imaginary gas that perfectly fits all of the assumptions of this theory. So these gases aren't, it's not how they function in real life, but it makes the math much easier to do. And real gases do not follow all of these properties. The first property says that gas particles are so small in relation to the distance between them that their individual volumes can be assumed to be insignificant. So if you think about a balloon full of gas particles, the balloon is a huge amount of space compared to the actual volume of an individual gas molecule. It's so teeny, teeny, tiny that it's not even significant. It's like if you were out in the Sahara Desert, your individual volume versus the whole huge desert is very, very small. And this property explains how we can compress gases. The second property says that there are no attractive or repulsive forces that exist between particles. And this is how we deal with gases, ideal gases, because it's much easier if they are not electrically attracted or repelled from each other. And we know from when we did bonding that's not actually true, but it's just much easier to deal with them like they don't attract each other. So as a result of that, gases are free to move in their containers anywhere they want to go, and they won't stick to each other. The third property says gas particles move rapidly in constant random motion. So as soon as they bounce off a wall, they just randomly move and bounce into something else. They're always going to travel in a straight line until they hit something. This random motion is affected by both the temperature and the volume of the container that the gas is in. Just like we've been talking about in the heat unit, temperature is the average kinetic energy of particles. And pressure is defined as force divided by area. So the more often the gas particles hit the wall of the container, the more pressure, the higher the pressure that you'll have in the container. Go ahead and flip over to the other side of your notes. Now it's time to talk about variables that affect gases. So the first variable we're going to talk about is pressure. And pressure, like we said, is force over area. And there are many, many units for defining pressure. We have atmospheres, which is the one we're going to use most often. So you could put a star by atmospheres. There's one called millimeters of mercury, which has to do with barometer, which we'll talk about in a second. There's bar, torr, pascals, and pounds per square inch, which if you ever filled up a tire before, that's the unit that we use when we talk about tire pressure. So take a moment to write all of those down. You may have to go outside of the box a little bit. Let's talk about atmospheres a little bit. So, say you're at the ocean and you're hanging out on the beach. If you're at the beach, the pressure on the beach, I don't know why you're not touching the land. The pressure on the beach is 1 atmosphere. We define atmospheres by sea level. Now, whatever beach you're at, there happens to be mountains nearby, steep mountains, like as high as Denver. So let's say you're in Denver, way up here, the pressure is going to be a lot less. I don't know what the actual atmospheric pressure is in Denver, but let's say it's 0.8 atmospheres. If you're on the ocean, you have the whole atmosphere above you, all of those gas particles pushing down on you, all the way up to space. So it's a lot of pressure. If you're in Denver, you're a little bit higher up. So there's less weight of the atmosphere pushing on down you, and the pressure is much lower. Let's say you go under the ocean and you're scuba diving. It's a wild day at the ocean, apparently. At sea level, the pressure is 1 atmosphere. But you've decided to go scuba diving, so now you're under the water. And you're pretty excited because this is your first scuba diving trip. And somehow you're doing it without a gas tank, which you're miraculous. So underneath the water, down here it might be as much as 5 atmospheres of pressure. And the further down you go, the pressure is going to increase even more. Somehow you're still happy about it. So maybe down here it's 10 atmospheres. Not only do you have all the pressure of all these gas particles above the ocean pressing on you, but you have the pressure of all this water on you. And if you're lower, you have even more. You may have experienced this in a swimming pool before. If you go to the deep end of a swimming pool and your ears pop, it's because your ears are adjusting to the change in pressure in that swimming pool. Pressure is measured with a device called a barometer. This video will explain to you how a barometer works.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, He believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
In the lab, we measured temperature in Celsius, but for all gas law problems, this is very, very important. All gas law problems must be converted to Kelvin. So Kelvin is based off of absolute zero, and absolute zero is where no molecular motion happens. Everything is completely still and there's no energy. In this video, we'll show you a little bit about that.
Are you ready to get cold? Are you ready to get really cold? Are you ready to get colder than most things in this universe have ever been before? Alright then, here we go. On a trip towards absolute zero! 4 degrees C. Cold enough to stop your milk going sour, but not cold enough for us. Minus 5 degrees C. Water has frozen, but not everything freezes at this temperature. Some things never freeze at all. Minus 89 degrees C. You might be starting to feel a little chilly. That's because heat flows from hot things, you, to cold things. Antarctica! There can't be anywhere much colder than this, right? Wrong. The beginnings of a new star. It comes in at minus 253 degrees C, or 20 Kelvin. 0 Kelvin is absolute zero! Temperature is really a measurement of how much things are moving, and out here, they aren't moving a lot. To go lower than this, we are going to have to get experimental! 4 Kelvin. 2 Kelvin. Weird, right? 0 viscosity weird. Below 1 Kelvin, particles slow towards their lowest possible energy levels. Most chemical reactions slow down or become impossible, although a few actually speed up. Below 500 nanokelvin, we enter a world of strange quantum effects, as matter becomes more ordered and seems to merge together to form waves. This is just about as close as we get to absolute zero!
We measure temperature with a thermometer.
But how can we measure their speed? Molecules are so tiny, we can't even see them, let alone clock how fast they're going. Wait a minute. There's something else we know about hotness. It not only causes a speed up of molecules, but this speed up causes matter to expand. So we could measure molecule speed indirectly by measuring the effect of that speed, the expansion itself. And that's exactly what a Swedish scientist by the name of Anders Celsius did in 1742. He took a liquid that expands quite a bit when it gets hot, mercury, and poured it into a little tube. He then put the tube into some freezing cold water, and the mercury contracted down to here. He decided to label this freezing point of water 0 degrees Celsius. Next, he put the tube into some boiling hot water, and the mercury expanded up to here. He marked this boiling point of water 100 degrees Celsius. Now he had a means of measuring the relative speeds of molecules. In other words, the relative temperature or degree of hotness of things. Comfortable room temperature is 20 degrees. But 30 degrees is a bit too hot. And minus 20 degrees is much too cold. Celsius could even take his own temperature and find it to be about 37 degrees.
The next variable used to describe gas is volume. We've talked about volume in class a ton. It's going to be measured in liters. It could also be measured in milliliters or cubic centimeters. And the last variable is the mole. And that stands on its own. That's a unit as well. Sometimes you might have to convert grams into moles in a problem.